Let's start today's video with number system. At first, we will talk about natural numbers. Natural numbers are the numbers that we use for counting. So, we can write the set of natural numbers n is equal to 1, 2, 3, 4, and so on. We use all these numbers to count things, and that is why all of these numbers are called natural numbers. The set of natural number is denoted by capital N. Let's talk about whole numbers. We have the set of natural numbers, and if we add a 0 to the set to the collection, then we will get whole numbers. Let me show you how. So here you can see that this part is already the set of natural numbers, and what I have done is that I have added a 0 to the set, and now this new set, this new collection is the collection of whole numbers, and that is denoted by capital W. Now let's talk about integers. Integers are a set of numbers that include all positive numbers, natural numbers, 0, and all negative whole numbers. So we can write the set of integers Z is equal to all the set of positive numbers, 0, and the negative ones. Let's start with the negative numbers. -3, -2, -1. This is our 0. And then we will write all the positive numbers that are the natural numbers, right? So 1, 2, 3, 4, and so on. So this is the set of integers, and it is denoted by capital Z. Now let's understand what rational numbers are. Okay, so rational numbers are the numbers which can be expressed in the form of p divided by q, where q is not equals to 0 and p and q are integers. The set of rational number is denoted by q. Let's take some examples so that we can understand what are rational numbers, okay? So for the first example, let's write 4. We will ask the question, can 4 be written as in the form of p divided by q? The answer is yes, because I can write 4 as 4 upon 1, and if I compare this with p upon q, p is 4 and q is 1, and q is clearly not equal to 0. So yes, 4 is a rational number. In the same way, the another example could be -6. Again, -6 can be written as -6 divided by 1. Again, I have my p as 6 and my q as 1, where q is not equal to 0. You can also take some other examples, right? 12 divided by 7, -4 divided by 9, or 0, because 0 can be written as 0 divided by 1, right? So all these numbers are rational numbers. Let me write some more examples. 0.125. I can convert this decimal to a fraction, okay? In the same way, 0.333, so on, 0.3 bar. We will learn how to convert these recurring decimals to fraction in the next section of this video, okay? So for now, all of these examples fall under the category of rational numbers. Now let's talk about decimal representation of rational numbers. So rational numbers can either be terminating decimals or repeated decimals. So there are two cases here. The first case is the rational number can be terminating decimals, or it can be repeated decimal. Now let's take some examples for both of the cases. Let's first see the terminating decimals. So the example would be 0.125. Here, this decimal number has been terminated at 5. There are no more digits written after 5, so clearly this number, this decimal part, is terminated at 5, so this is called the terminating decimal. If you convert this decimal to a fraction, it will be equal to 1 by 8. And another example can be 0.37. Here again we can see that this number is terminated at 7. There are no more digits written after 7. So again this 0.37 is a terminating decimal. This 0.37 can be written as 37 divided by 100. Okay. Now let's see what repeated decimals are. The repeated decimals are often called recurring decimals. That is because of their nature. For example, I can write 0.3333 and so on. Unlike terminating decimals, repeated decimals or recurring decimals do not end at a particular digit after the decimal. The difference can be seen very clearly. If I write a terminating decimal like 0.3, this is a terminating decimal because after 3 there are no more digits present. But here we can see that after every digit there is a 3 following that digit, right? So this one here is a repeated decimal, or we can call it a recurring decimal. There could be one more example. I can write 0.353535. So this one right here, we can see this 3 and 5 both are repeating in the same sequence, one after the other. So this one is also a recurring decimal. If you are curious, we can understand that this one can be written as 0.3 bar and this one can be written as 0.35 bar. Both of these decimals can be converted into fraction. Here this will be 1 by 3 and here this will be 35 divided by 99. Do not worry if you do not understand or do not know how we can convert these decimals to fractions. We will take many questions in the upcoming sections and we will learn how we can convert these repeated decimals to fractions. Let's talk about irrational numbers now. So the numbers which cannot be expressed as p divided by q, q naught equals to 0, where p and q are integers. So all the numbers which are not rational are irrational. Irrational numbers are non-terminating and non-recurring decimals. Let's understand what this term means, non-terminating and non-recurring. For that, let's take some examples of irrational numbers. Our first example can be root 2. Okay, so if you use your calculator to find the value of root 2, you will get something like 1.41422135, and this will go on forever. In the same way, the root 3 will be 1.7320500807 and so on. The very famous irrational number pi is equal to 3.1415925, and again this will go on. So all these numbers, you can see clearly that these numbers are not ending. they go on continuously, and there is nothing that is reoccurring again and again. So there is no recurring. No digit is occurring in a similar fashion again and again, like what we had already saw with rational numbers. Okay, so this is a rational number where the numbers are non-terminating and non-recurring in nature. Let's talk about real numbers now. A rational or irrational number combined are real numbers. So let's understand this. See, if we have a box containing all the rational numbers, this one, the first box, and then we have another box containing all the irrational numbers, and now we have found a bigger box that contains all the rational and all the irrational numbers. So this box will be the box of real number, because real number contains all the rational numbers as well as all the irrational numbers. Okay, now let's understand a very important concept: prime numbers. So a prime number is a positive integer which is divisible by itself and by 1. So let's take some examples so we can understand what prime numbers really are. So let's talk about 2. 2 can be divisible by itself and by 1. There is no other number which can divide 2 completely. In the same way, 3, 5, 7, 11, 13, and 17. So the list goes on. All these numbers are prime numbers. So let's check if 16 is a prime number or not. See, we can clearly see here that 16 is divisible by 1. 16 is also divisible by 2, 4, and 16. So for 16 to be a prime number, it should only be divisible by itself and 1. But here we have 2 and 4. Both of these numbers divide 16 completely. So 16, by the definition of prime numbers, is not a prime number. Okay? So let's talk about 2 important points that one should remember about prime numbers. First point is 1 is not a prime number, okay? 1 is not a prime number because the definition of prime numbers is basically all the numbers which are greater than 1. So 1 is not a prime number. Second point is 2 is the only even prime number. So what are even numbers? Even numbers are all those numbers which are divisible by 2. So among all the even numbers, 2 is the only even number that is prime. So if someone asks you what is the only even prime number, 2 will be your answer. Now we will learn to express a recurring decimal as fraction. For that, let's take an example. So this is the question. Write the recurring decimal 0.4 bar as a fraction. Clearly this 0.4 bar is a recurring decimal, and what we need to do, we need to change this recurring decimal to a fraction. Let's solve this question. So let's solve this question. Let's assume that x is equal to this recurring decimal, that is 0.4 bar. Now I can write this 0.4 bar as 0.4444 and so on. Let's call this equation 1. Now what we can do, we can multiply with 10 at the both side of this equation. If we multiply 10 with the both side of the equation, it will be 10x equal to 4.444, right? Because here if I multiply with 10, this decimal will shift towards right one place, and that will give me 4.444. Now this part can be written as 10x equals to 4.4 bar, right? Let's call this equation 2. Now subtracting equation 1 from 2. Let's subtract equation 1 from 2. So equation 2 is 10x equals to 4.4 bar, and equation 1 is x equal to 0.4 bar, and we need to subtract these two equations. Let's subtract it. So this part will be 10x minus x, 9x equal to, here it will be 4.0. Here I can write x is equal to 4 divided by 9. So this is our answer. So 0.4 bar can be written as 4 divided by 9. Now let's solve the next question. Write the recurring decimal 0.17 bar as a fraction. Let's see how we can solve this. We'll assume x is equal to 0.17 bar. So clearly this can be written as 0.17777 and so on. Okay. First step is to multiply 10 to the both sides, because here there is only one digit that is recurring again and again. So we will put 1 0, or we will just raise a power of 1 to 10. Had there been two digits recurring, repeating itself, we would have put the power 2. If there were 3 digits repeating, we would have put the power 3. Here, the only digit that is repeating itself is 7. So we have put a power of 1 to 10. So 10 raised to the power 1 is already 10. So what we will do? We will multiply this equation, both sides, with 10. It will be 10x, and this one will be 1.777. Again, I can write this as 10x is equal to 1.7 bar. Let's call this equation 1. Now, what we will do? We will try to multiply 10 again to this new equation that we have. So it will be 10 multiplied by 10, 100x is equal to 17.777 and so on. If you multiply this with 10, the decimal will shift towards right one place, and it will give you 17.777, right? Now this can be written as 100x is equal to 17.7 recurring, and let's call this equation 2. The aim here is to find the same repeating digit after the decimal. See clearly here in equation 1, after the decimal I have 7 recurring, right? In the same way, equation 2 also has 7 recurring. So if I subtract these two equations right now, the part that is written after the decimal will get cancelled out. So that is our aim for this question. That is how we will solve this. So now if I subtracting 1 from 2, I will get 100x equal to 17.7 bar. This is the second equation, and I will have to subtract equation 1 from it. So equation 1 is 10x equal to 1.7 bar, and now I will subtract it. 10x will be subtracted from 100, it will be left with 90x, and here 17 minus 1 is 16, right? So clearly from your x is equal to 16 divided by 90, you can simplify it further to 8 divided by 45. So this one is our answer for this question. Let's solve the next question. Write the recurring decimal 0.63 bar as a fraction in its lowest term. It means that you need to simplify the fraction as much as possible. You must show all your working. Okay, so let's try to solve this question. We know what to do. Let's assume that x is equal to 0.63 bar. Now, clearly, if you had followed the second question that I had just solved, I had given you a very crucial information. In this question, there are 2 digits that are repeating after the decimal. So what we need to do, we need to put the power 2 to 10, that will be equal to 100. And this will be used to multiply this current equation, and this will be used to multiply this equation with. So I can write this as x is equal to 0.636363 and so on, right? Let's call this equation 1, and now as we have already planned, we will be multiplying 100 with this equation both sides. Now let's multiply 100 to the equation. This will be 100x equals to 63.636363 and so on, right? Now I can write this as 100x is equal to 63.63 recurring. So clearly, if I call this equation 2, you can compare from equation 1 and equation 2 that the right hand side, that means the digits after the decimal, are same in both of the numbers. Here it is 63 recurring, and in the same way in equation 2, this one is also 63 recurring. So clearly I can subtracting 1 from 2. So if I subtract 1 from 2, I have 100x equals to 63.63 recurring as equation 2, and now x is equal to 0.63 recurring is my equation 1, and I need to subtract, right? So let's subtract. 100x minus x will give you 99x, and this will be 63. So here if I can solve this, x will be equal to 63 divided by 99. So this one, 63 divided by 99, is not in its lowest term right now. We can simplify it further. So this will be, if I divide it by 9, this will be 7, and this will be 11. So 7 divided by 11 is our answer for this question. And that brings us to the end of today's lesson on decimal representation of rational numbers. We have learned how to identify terminating and recurring decimals and how to convert them into fractions step by step. And now it's your turn to take on the challenge question. Write the recurring decimal 0.127 bar as a fraction. Okay, take your time, show all your steps, and leave your answer in the comments. Okay, if you found today's video helpful, don't forget to like, share, and subscribe to Ace Maths for clear concept-based math tutorials. And don't forget to hit the bell icon so you never miss a math trick or exam tip. Okay, so keep practicing, and I'll see you in the next video.